Yeah.
Miss Gunjan Sharma, please, are you there? Please start the introduction.
She has problem with the connection.
Maybe, sir, I am contacting with her.
Oh, yes. Now the Mrs. Sharma, you can start. Unmute, please. Unmute.
Please unmute yourself.
Welcome to fourth e-learning program of SPM PCR, and thank you for all for joining for today's webinar. I am Gunjan Sharma, who is working as a medical physicist in Govt Medical College, Amritsar, Punjab, India, and I have completed my studies from Residency in the Trust University, New Delhi. I am moderator for today's lecture. I welcome you all to 8th lecture of fourth e-learning program. This is to inform you that there will be an examination at the end of 8 lectures, 1 hour each, and a group discussion which is tomorrow. And this is a program which has been evaluated by EBA MD as a CPD event for medical physics at EQF level 7 and awarded 32 CPD credit points and 24 CPD credit points for those who don't sit for the examination. We are pleased to inform you that over 200 candidates registered for this e-learning program, and the selection committee has chosen over 85 participants from 27 different countries. And now I'll give the introduction about SPM-PCR. It is a project by LO Bogan Trust, incepted in the year 2016, with an aim to create a skilled manpower in the field of medical physics, especially in the South Asian region. Since then, it is organizing meetings, seminars, webinars, workshops, hands-on training, and many e-learning programs. SPM-PCR has already implemented 3 successful e-learning programs with accreditation from EBA-MD, that is European Board of American, accreditation of the medical physics, and IOMC. The unique design of SPM-PCR training and e-learning program already make very popular for teaching, learning, and sharing knowledge between the medical physics of different origins. Its motto is quality education for the patient benefit. This vision of imparting quality education to the budding physicists all across the globe, specifically in the South Asian region, belongs to Chairman Professor Dr. Ghulam Abu Jagaria, who is present with us today. He has been the cornerstone of SPM-PCR, and its all programs are the product of his efforts and the team that he has built. He is a former chairman, chief medical physicist of the Department of Medical Radiation Physics, Bunch Hospital in the University of Cologne. He is currently professor at the University of Applied Sciences, Germany. He has 35 years experience. He has published over 100 research papers and supervised various theses. Now I would like to request Professor Dr. Ghulam Abu Jagaria, the chairman SPM-PCR, to deliver a few words as a welcome speech to all the participants.
Thank you so much, Mrs. Sharma. This is our last but not least lectures, and we have today a very good expert. It is my colleague from USA, Professor Dr. Ho-Ling Anthony. You will enjoy it. I know him very well. He's actually an international expert, and he gives lectures all over the world. We are very happy that he's there. And our participant is all over of the South Asia and other countries. And this is a very important topic. Yes, MRI is a very potential diagnostic tool, and every medical physics should know very well. You can learn what you like. In MRI is a huge potential. and Professor Louis can explain you everything very well. Thank you once again for your participation. I hope you will also take part in the examination, and then you will get the certificate. Thank you.
Thank you so much, sir, for your inspiring words. So today's topic is MRI quality control and image quality management, which is going to be delivered by Professor Louis Anthony from University of Texas, who is working in a Kuniva General Hospital, Geneva, since Jan 2019. He is a professor in Department of Imaging Physics, Division of Diagnostic Imaging in the University of Texas. He is director also in Imaging Department of Imaging Physics and the Division of the Diagnostic Imaging, Houston, Texas. He is also the member of Education Committee of Health Professional Programs and the Diagnostic Radiology. So continue your lecture, sir. It will be very knowledgeable for us. So please share your knowledge with us. Floor is all yours. You can start your presentation.
Thank you for your kind introduction. Let me try to share my screen first.
And it is a request to all the participants. You can please type the questions in chat box. We will take the questions answer session in the last. And please mute your microphone so that there is no disturbance to our speaker.
So are you seeing my slides? I just played the slide.
Yes, sir, we can see.
Okay, everything is clear, everything's right? Okay. Okay, so I'm going to start. Yeah, first of all, welcome to my class. I'm very happy to have this opportunity to teach MRI. And so today I'm going to cover a very practical topic, which include MRI quality control and also the quality management. This is the outline. First, I will cover a very practical topic about equipment performance evaluation, which include acceptance testing and quality control testing. And then I will give a broader overview about quality management program that include a complete quality management program. You will see what I mean, which is not just the QC or testing. And then, as you can see, one of the components of quality management is image quality and MRI sequence optimization. I will briefly touch on this topic. So first about testing an MRI scanner. My contents are basically from these two documents, based on the two documents. And of course, I will provide some example from our own experience. The first document is the AAPM Report 100. This includes a very complete list and guidance about testing that are needed for acceptance and also quality assurance. And then, so AAPM Report 100 is what I consider a go-to for everything I need to know. And the other document is ACR, American College of Radiology, MRI Quality Control Manual. So maybe some of you know the sites in MRI, many sites have their MRI scanner accredited by ACR. That's not a requirement, it's not regulation, but it's good to get accredited. So if your site want to accredit your scanner, then you have to follow this quality control procedure. So this is what I consider as a basic, as what must be done to ensure good quality. So in my talk, you will see a reference from both of those. So let's give a broader scope about acceptance testing of MRI scanner. When we receive a new MRI scanner, what do we need to do? Actually, what we need to do is before the MRI scanner arrives, Okay, so before the MRI installation, we need to have a vibration measurement, RF shielding measurement. That's a MRI room shielding. And then after the installation, there are 5 components of the testing. The magnetic fringe field mapping, I will give some example later. And of course, inventory is needed for all the new equipment, general system checks. And then MRI scanner system test. This part is what we usually call system testing or QC testing. Also, we do this during annually. And then advanced MRI system testing. If we have advanced applications, we will do this part. So some details about general system checks. We check mechanical system, emergency system, patient monitoring, and other third-party equipment. For the MRI system testing, the scanner itself, we test the static magnetic field, RF field, the gradient subsystem, and also combined gradient RF subsystem, and global overall quality. And for advanced MRI testing, typically that include ultrafast imaging like EPI and spectroscopy test. So this is before MRI installation. I mentioned the RF shielding test is very important. I think most of you, if you have learned MRI, you know the MRI need to be shielded by RF. So basically that's a copper around the room, and RF cannot go out and it cannot come in. So once this shielding is done, we have to test the integrity of the shielding. The testing is by transmitting an RF at a different frequency from outside. And inside, remember the scanner is not there yet. So in inside, we use RF antenna, just check different locations. So this is a drawing of a scanner room. You can see the spot 1, 2, 3, 4, 5. Those are the locations they are tested. And then after that, we will receive a report. Usually, this testing is done by manufacturer, but physicists need to be present to make sure they do the right thing and making sure the result is either in criteria or it's not. If not, then we need to make sure they are corrected. So this is just a part of a report. I'm trying to show you we are testing different frequencies. Like here, show you 76. Sorry, the font size is probably small, but just idea. This is about 70 megahertz. That's 100 megahertz. This is 128 megahertz. For 1.5T, at least we need to test 1.5T central frequency, which is 64 megahertz plus higher frequency, usually more than 100 megahertz. For 3T, we want to make sure to test up to 3T central frequency, which is 128 megahertz plus higher, around 150 megahertz. And those are different locations. So from 1 to 8, those locations are shown here. And the right-hand side highlighted here are the attenuation. The requirement is a 100 dB attenuation. And you can see the yellow highlights just 100, whereas the red is fail. So it's 89 dB, that's not enough. Okay. And after MRI installation, there are magnetic field. So so-called fringe field is the magnetic field extended outside of the MRI. I think everyone, if you have learned MRI, you know 5 Gauss line is very important for MRI safety and the control. So we have to map, once the scanner is installed and the field is ramped up, we have to map the fringe field, at least to map where are the 5 Gauss line. To do this, you need a Gauss meter like that, and then just go through around the scanner. Usually we will have the drawing from the vendor. So ideally, the drawing already shows us where are those Gauss lines. And then we can just measure at different locations. Like here is the red curve shows the 5 Gauss line of a 1.5T scanner, and on the right-hand side is a 5 Gauss line of a 3D scanner. Typically, we will map the complete 5 Gauss line and plus the location at the console, the working area. So those are acceptance testing. We don't do those annually, okay? So what we do both during acceptance testing and also annually are the scanner testing. So here I already mentioned the major items for scanner testing, those 5 items. So just a little bit more details for magnetic field. We measure field homogeneity. So that's a spatial homogeneity. And then the field drift over time. And for the RF subsystem, we basically monitor the transmitter gain, calibration, and stability. For the gradient subsystem, we make sure the geometric accuracy and linearity are good because they will be affected by the gradient subsystem. And also eddy current compensation. This is typically measured during the service, so the regular preventive maintenance. For the combined gradient RF subsystem, mainly that's a slice prescription, so slice thickness and spacing. For the global system testing, those include signal to noise ratio, percent image uniformity, high contrast spatial resolution, low contrast detectability, and percent signal ghosting. And for the ultra fast, so those are advanced applications. Ultra-fast imaging include ghosting, geometric distortion, EPI stability, and spectroscopy, including VOI, volume of interest, location, accuracy, and spectral quality test. So today, of course, I'm not able to, during the time, because of the time limitation, I'm not able to go through all the details of each testing. This is a lot. This will be probably several days of hands-on training, okay? But I will go through some of them, those important ones, just highlight those important ones and then give some examples. So far I mentioned acceptance testing. So how about quality control? Quality control, I mentioned, we basically, most of the sites in the US follow the ACR guidance. And ACR require technologists to perform weekly testing, okay? Again, apologize for the small font, but I will read through. Weekly, technologists need to perform setup and table position accuracy, central frequency monitoring, monitoring transmitter gain and attenuation, measure geometric accuracy, high contrast spatial resolution, low contrast detectability, artifact evaluation. If they are still printing film, they need to do film printer QC and a visual checklist. And annually, this is what physicists need to perform. So in addition to the weekly QC, physicists will also perform magnetic field homogeneity, slice position accuracy, slice thickness accuracy, RF coil check. RF coil check include signal to noise ratio, image uniformity, percent signal ghosting, and also the monitor, the soft copy QC, and also MRI safety program assessment. This is about the weekly Technologist QC. I have read through the items that needs to be performed weekly. Okay, this is the only slide I have to cover Technologist QC, but I think physicists need to understand this and set this up to help technologists and also help to establish baseline. But all other slices I will mention are mainly covering the Physicist QC. Also in this table, list the time involved. So if you add everything up, if we exclude the film printer, probably not many places are printing film now. So if we exclude the printer, it's about 20 minutes weekly for technologists to perform. Okay, the setup including scanning, that's estimated to be 7 minutes. And other times are for visual checklist, 5 minutes, or other very simple measurement. At our site, and also many major academic institutions in the US, technologists only need to perform the setup part. So they set up the phantom and scan, and then push the image to a website, to a location. Then we have software to automatically process everything. So we are doing this actually daily. At MD Anderson, we have 30 clinical scanners. So on each scanner in the morning, technologists arrive at about 6 a.m. They will just set up the phantom and scan. That will be done within 10 minutes. And then they push image to a location. Then we have a system that will process everything automatically. Here, I just show you, this is a daily result of center frequency and transmitter gain. This is nothing but a recording from the data. When you start to scan anything, the scanner will automatically calibrate and adjust center frequency and transmission gain. And then you just record the number. You don't need to do any measurement. But just by monitoring the numbers, you will see there are system issues when they occur. Okay. In this case, initially we saw transmission gain increase. So that tells us the transmitter may have some issue. And then followed by central frequency drop. And then finally, it goes outside of our own baseline. So physicists need to establish a reasonable baseline. Usually we use about 3 standard deviation of the baseline measurement. So when it goes up, and then we asked the service to investigate, and we found that the body transmission coil was bad. So we had to replace the body coil. So this was found before we found any artifact in the patient image. That's the purpose of QC. Okay, about physicist responsibility. I have mentioned this table already. So physicists need to do annually testing of all the weekly testing plus the additional testing. So that's the annual system evaluation. But besides that, our responsibility also include establish baseline and action limit for the Technologist QC. Our responsibility also include purchase specification and acceptance testing. So I have mentioned items for acceptance testing. For any kind of scanner testing, we will need phantom to scan. And there are many kind of phantoms in MRI. Here I just try to make a brief summary. ACR phantom now is very common in the US. Almost every scanner has ACR phantom. This is very good for general quality control. So this is ACR phantom. And in my following talk, I will give example. All my example, I will provide one with ACR phantom. And then for the magnetic field homogeneity, we need to use a large phantom that's usually provided by vendor. Okay, so here is a large phantom that can be used to test the field homogeneity. And for RF coil testing, they are specially designed phantom. Usually they are homogeneous phantom, but with different shape. So the purpose is to test various kind of RF coils. For example, spine coil, body coil, knee coil, shoulder coil. You need to fit the shape of the coil. So that's why the phantoms are different, but they are basically all homogeneous. And then we have spectroscopy phantom. Within spectroscopy phantom, we need to have chemicals that can mimic tissue metabolism. So I will show you one example of the spectroscopy phantom result. And there are other specific purpose phantoms. For example, geometric accuracy phantom. Here is a homemade geometric accuracy phantom. There are also you can also purchase from different vendors about this kind of phantom. Usually those are designed for radiation therapy treatment planning purpose. For example, the gamma knife quality control. And we have quantitative imaging phantom. Here I'm showing a phantom recently developed by NIST and ISMRM. You can see they are T1 arrays, T2 arrays. So those phantom, they can allow measure the accuracy of T1 measurement, T2 measurement, and other quantitative imaging. And also there can be flow phantoms or perfusion phantoms, different purpose, special purpose phantoms. So ACR phantom is a very important one. So I want to describe a little bit more. This is what the ACR phantom look like. So you place this in a typically a head coil. This is a chin, this is a noise, this is a nose. And the phantom size is 148 millimeter in the length and 190 millimeter diameter. And the content has nickel chloride. This control the relaxivity, so T1 and T2, and also sodium chloride, that this control the conductivity. Both properties are important to make a proper MRI measurement. And ACR has this phantom test guidance document that provide details about how to use this phantom. So ACR phantom can provide typically the 7 kind of testing: geometric accuracy, high contrast spatial resolution, slice thickness accuracy, slice position accuracy, image intensity uniformity, percent signal ghosting, and low contrast detectability. I will give an example for each one of them. And the proper scan of the ACR phantom include at least 3 scans. First, a sagittal localizer. This is a single slice acquisition using a spin echo sequence. The image will look like that. Okay, so this is a chin, this is a nose. And then on this sagittal image, we prescribe the axial slices, 11 slices. The first scan is ACR axial T1 scan. That's a spin echo sequence with TR 500, TE 20 millisecond. 11 slices, 5 millimeter slice thickness and 5 millimeter gap. And the pixel size should be 1 millimeter by 1 millimeter. So typically we set field of view 256 with 256 matrix. So the pixel size will be 1 millimeter. And then the ACR T2 is a dual echo spin echo sequence. So there are 2 TEs with a long TR, 2000 TR. And the 2 TEs, the short TEs will be proton density and the long TE will be T2 weighted image. So we only look at the second TE, the second TE image, which is a T2 weighted image. The same number of slides and the slice location, prescription, and also the same metric size and resolution. So for weekly test, we only do 2 scans, the sagittal localizer and the ACR T1. For annual testing, we do 3 scans, sagittal localizer, ACR T1, and ACR T2, okay? If the site is applying for ACR accreditation, then 2 additional scans will be required, which is site T1 and site T2. So basically we use a site protocol to scan the ACR phantom. So one of the testing is a table position accuracy. This is included in the weekly testing and also annual and also acceptance testing. This is very simple. We just test the axial laser. So basically here is the center in the SI direction, the center of the phantom. If we laser a landmark at the center of the phantom, then here should be the center of the image. That's the idea. Okay, if we landmark at the center of the phantom, then on the image, the center of the phantom or the laser landmark should be at the center of the FOV. If it's not, then the laser has an issue, right? So actually this test doesn't require ACR phantom. We can use any phantom just to make sure we laser landmark at the center of the phantom. Then that can be used, that can be tested. But here I'm showing the ACR phantom. So here is the center. And after we image, you just look at the coordinate of the center. So here shows you 0. This font is very small. So this is a perfect case. That means the error is 0. But if this is 1 or -1, that means the laser is inaccurate by 1 millimeter. ACR has very generous criteria, which is ±5 millimeter. Okay, that's because for diagnostic radiology, the laser landmark is not very critical. For therapy, it's a different story, but for diagnostic imaging, typically, if you are off by 5 millimeters, it's still within the field homogeneity area. So the image quality will not be affected. So here I'm showing you a daily table positioning result of one of our scanner. And you can see starting from sometime about March this year, the table position accuracy start to change. However, it's still within ACR limit, so we didn't call the service. And at certain time, the service came in. Actually, this is a routine service. We didn't call them. This is just a PM, quarterly PM. And after the PM, the table accuracy becomes very bad. That's because when they did the PM, they need to take the cover off, and the laser is on the cover. So when they put it back, they didn't calibrate carefully. So now we really need to call the service. So when the service came in, they adjust this laser, and then it's just around the border of the ACR limit, 5 millimeter. And then at this point, we call the service. We say, well, it's about 5 millimeter. Please come in when you have a chance. This is not critical. We are not going to call the scanner down. So at some point, just I think a few days ago, they came in and adjust this to be within the limit. Okay, this is, now we move to the scanner itself. The table positioning is a mechanical part, is the laser, it's not the scanner itself. But now let's move to the scanner. The first topic is main magnetic field. Main magnetic field, this is to monitor the drift over time. Like I mentioned, we just put a phantom in the scanner and then scan, then we record the central frequency, okay? But the critical thing is we want to monitor the change. So we have to use the same phantom and use the same sequence and the same setup every day or every week, okay? In our case, since we scan ACR phantom every day, so we just use that. So we record the center frequency every day. This is the AAPM criteria. It's 1 ppm per day during acceptance testing. So on top, I'm showing you a new scanner we installed in about March. And then you can see the central frequency gradually change. So the magnetic field gradually change. This looks like terrible, but if you look at the number, it's actually 1 ppm per month. So this is perfectly fine. We don't need to worry about it. Okay, 1 ppm for 1.5T is 64 megahertz per month. And well within the criteria, 1 ppm per day, recommended by the AAPM. AAPM also recommend a typical of 0.25 ppm per day after 1 to 2 months of operation, okay? This is just a recommendation. Here I'm showing you an old scanner on the lower part. I'm showing from the September of last year. It has been very stable, but recently, early March, the central frequency start to increase. If we look at the number, it's only 0.15 ppm per week. Okay, still within the ACR the AAPM recommendation. However, we think this is now okay because the scanner has been stable for so long time, and this change is very consistent change. So we did call the service, and the service came in and found pressure increase. The call head is bad. Okay, if they don't change the call head, there's a risk of quench. This will be very serious. So they come in immediately and replace the cold head. And after that, the field comes back to stable. So this just highlights the importance of monitoring of the central frequency or the magnetic field. The next is spatial homogeneity of the magnetic field. This is very important for image quality, and this is required for physicists to test annually, every year. And just a brief introduction, the field variation is usually described by ppm or hertz over a given diameter spherical volume, or DSV. So basically we use a large homogeneous phantom, and we can look at the spatial homogeneity within a certain diameter of spherical volume. And the standard method is to use the gradient echo sequence and do phase mapping. We look at the phase image. That's a standard method. And acceptance criteria is vendor and model dependent. So for example, even within vendor, different model can have different criteria, whether it's a narrow bore or wide bore scanner, their homogeneity criteria are different. But anyway, AAPN also provide a general recommendation about half ppm room mean square for 35 centimeter diameter spherical volume. Okay, here I'm showing you two results from vendor. So when vendor, they come in to do routine preventive maintenance, they usually will check the shim, and that will provide the homogeneity result. So on the left-hand side is an example from a G3T scanner. You can see they look at different spherical volumes. So 50 diameter, 45, 40, 30, 20, and measure peak to peak and room mean square. Okay, and here also it listed other limit. So for example, 30 centimeter diameter, the measurement was 0.067 ppm, and the criteria is 0.5 ppm. This is very close to the recommendation by the AAPN. On the right-hand side is an example from a Siemens 1.5T. They don't provide the measurement of different diameters, but they just put the fixed constant phantom, the same phantom every time, and measure the homogeneity within that phantom. So in this case, the peak-to-peak measurement and room mean square measurement are both listed, and this is the criteria. So those are the vendor's measurement. How do we measurement? How do we make measurement as a physicist? Both AAP and ACR recommend 4 methods. Okay, the most easy method is a spectral peak method. We just put the homogeneous phantom there and get a spectra, and then look at the full width at half maximum. And if we do a little bit more, we can use the bandwidth difference method. Bandwidth difference method involve doing 2 images with the same setup but different bandwidth, and measure the diameter of the image, and then plugging into this equation, then we can get the overall homogeneity. Okay, so either of those 2 methods, they provide overall homogeneity. They cannot tell you which location has a bad homogeneity. So the 3rd and the 4th method, phase map method, can provide us information about where in the area has bad homogeneity, because that provides a homogeneity map. The most standard method I mentioned is the phase difference map. And here show an example. We do a gradient echo image with 2 TE, so short TE and long TE. This is not a magnitude image, but those are the phase image. And then we can subtract the 2 phase image and then get a phase difference map. The phase difference map, you see there are wrapping because phase is limited by 2 pi. So we have to perform a phase unwrapping And this is unwrapped phase map. And then with that, we can calculate the field homogeneity is proportional to the phase difference. So this involves some computer programming, or it's not very straightforward. That's why also the first three methods are recommended. So about the geometric accuracy, basically, it's affected by the gradient linearity. And we can use a phantom with known diameter like ACR phantom, or we can use a uniform grid or whole phantom like the phantom result shown here. So here I'm showing you two images. One is scanned at isocenter, z equals to 0. Another image is scanned at off isocenter, 22 centimeters from isocenter. You can see a lot of distortion at off isocenter because the gradients not linear in this area. So APM criteria is the percent geometric distortion should be less than 2%, or should be less than 2% for treatment planning purpose. When we use the ACR phantom, we measure the three images. We just measure the overall diameter or the length of each image. So the first localizer, we just measure the length. It should be 148. It's a physical length. And then we use a slice 1. Slice 1 represents a little bit of isocenter. So the AP and the left-right direction. And then slice number 5. Slice number 5 is close to isocenter. We make 4 measurements. So those ideally should be 190 millimeter. So ACR criteria is plus minus 2 millimeter for each of those measurements. And also the measurement will be depending on window width and window level. So ACR required the measurement is made by this setting. The window width should be about the average signal of the water, and the window level should be half of the average signal of water, which means we are measuring at the full width at half maximum. And here shows you a result from one of our scanner. You can see clearly. So there are 5 lines. The 5 lines are the 5 measurements on the slice 5. Slice 5 I show here. There are 5 measurements. Okay, and you can see the geometric accuracy is off at this time point. So what happened was this was a routine PM. So after the PM actually, so the engineer came in to do a service, and after the service, they did some gradient calibration, but the calibration was not in a good condition. So actually it made the geometric accuracy worse. However, it's still within the ACR limit. Okay, it's within the red dashed line here are 2 millimeter plus minus. So they are still within ACR limit, but in our institution, we require 1 millimeter, or we try to make 1 millimeter. That's better than ACR limit. So we asked the engineers to come in to recalibrate, but make another direction worse. This direction is better, but other direction was worse. And then they came in again and then make everything good. The next measurement is slice thickness. Slice thickness is, in principle, we can use a cross ramp. So if there's a ramp in the image, then the length of the projection of the ramp will represent the slice thickness. And when there's a cross ramp, then there are 2 measurements. For example, here, those are represent image of the projection of those ramp. So the length of the ramp will representative of the slice thickness. And this is the equation, general equation. And with ACR phantom, the ramp ratio is 10/1. So if we plug in that equation, we found it simplified to this. So A and B are the length of the measurement. And then we use this equation, we can calculate the measured thickness. This is ACR criteria, which is less than 10%. And the APN criteria is less than 10%. ACR criteria is 5 plus minus 0.7 millimeter. Remember, ACR protocol is 5 millimeter slices. So if it's between 4.3 and 5.7, those are good.
Sorry for the interruption, sir.
Sorry?
So we have limited time. Please try to complete your slides timely. Sorry for the interruption.
Is that a question for or just remind me about the time?
Sir, it's
Yes,
just a reminder about the time. We have 40
Okay,
minutes left.
Yeah, that's fine. Yeah, I think I rather to go slow, and if at the end some of the topic I cannot cover, that's fine. I put a more important and practical topic in the front.
Okay, sir, please.
Yeah, the next test is about slice position accuracy. Slice position accuracy are based on the two ramp here. So we prescribe the slice 1 and the slice 11 across the ramp. So if they are accurate, then the length of the ramp should match. But when they are not matched, then that's the slice accuracy issue. So the ACR criteria is the bar difference should be less than 5 millimeter. Because the ramp are 45 degrees, so the 5 millimeter represent accuracy of 2.5 millimeter. Okay, the next is very important test. That's the SNR, signal to noise ratio. Signal to noise ratio would depend on RF coil. So for different RF coil are different, and also phantom positioning are different. So when we make the measurement, we want to make sure the phantom positioning and phantom use are consistent. There are many ways to measure signal to noise ratio. The most standard way is the NEMA method. The NEMA method requires two measurements, two scans. Okay, like here, I'm showing you the first image and the first scan, the second scan, using the same setup, same everything. And then you average them, and then you do a subtraction, okay? From the average that provide the signal, the subtraction provide the standard deviation within the same region of interest. And then because the subtraction will enhance the noise by square root of 2, so we want to correct that. So we multiply square root of 2 to calculate the SMR. That's very simple equation. However, in many of the situations, NEMA is not practical because we need to make two measurements each time. There are so many coils. So there are other methods developed. Most simple method is just to look at a single image, and then we assume the background signal. When there's no signal, the distribution should be a rising distribution. And with a rising distribution, the SNR is calculated by the average signal within the phantom and divided by standard deviation outside of the phantom, so background, multiplied by 0.655. Here shows you the daily SNR result, and then at a certain point, it certainly drop quickly to a low SNR, and this definitely is caused by a bad coil. So we put a coil out of service and request for replacement. The SNR should be measured for all coils. This is annual testing. Okay, for annually, we need to measure all the coils. For surface and phase array coils, ROI should be shown or documented. So we make sure we are making a measurement at the same spot every year. And for phase array coil, because there are many elements, SNR should be obtained for each coil element. And the next test is percent signal uniformity. So basically, we image a uniform phantom. This is an example from the slide 7 of ACR phantom. And then look at the area with high signal and area with low signal. So high minus low divided by high plus low, that's the non-uniformity. And uniformity is 1 minus that. So ACR requirement is the image uniformity should be more than 87.5% for all scanners. For 3T, uniformity can be worse because of the dielectric effect. So the criteria is 82% for 3T. So here shows an example. We typically use a quadrature coil for our daily QC on this scanner. The uniformity is pretty good, but at a certain point, the quadrature coil is bad. So we use a multiple array coil. And of course, without intensity correction, the uniformity will be bad. And then if we apply an intensity correction, it will be good. But we decide this is a temporary, so we keep that without intensity correction. And then after the new quadrature coil arrives, it goes back to the normal range. Another test is percent signal ghosting. So we know ghosting comes from the instability of the system, and it will show up in the phase encoding direction. So if we put 4 ROIs, left, right, and anterior, posterior, one of the directions should be phase encoding and the other should be frequency encoding. So we average one direction and the other direction and minus the 2, that gives us the amount of ghosting. So this is definition of the percent signal ghosting. And in this case is 2.5% is a criteria by ACR. And in this particular scanner, I'm showing you a mobile MR. It's a trailer. So the MR is in a trailer next to the street. So sometimes we really do get a lot of ghosting because of the instability issue of the mobile MR. And the high contrast spatial resolution using ACR is very convenient. From the slide number 1, there are 3 modules, 1.1, 1.0, and 0.9. And each one has two parts. On this part can measure the resolution on the left-right direction, and the right-hand side can measure the resolution in the AP direction. The criteria is at least the theoretical pixel width should be able to observed. So I mentioned the protocol is scanning at 1 millimeter. So we want to make sure the resolution actually reach 1 millimeter in both directions. And in terms of low contrast detectability, ACR Phantom has 4 slices. The last 4 slices, 8, 9, 10, and 11, they have object of different contrast. Okay, 11 has the highest contrast, 5.1%, and slice 8 has the lowest contrast, 1.4%. So each slice will have 9 groups, so we can score 9. If we score 10 groups, so the maximum score is 10. And over the 4 slices, the maximum score will be 40. With the 40 scores, ACR criteria is 9 for all the scanners. However, we know the low contrast detectability should be better with a higher SNR and higher field strength. So for 3T, the criteria is 37 scores. Okay, here also shows some typical scores. So that's the recommended scores at different field strength. So for example, 1.5T scanner is very common. The minimum of for 1.5T is 9, but that's too easy to achieve. That's too easy. So the recommended score is actually 36. Okay, and this is also scored weekly. For weekly number, if it's reduced by, in any given week, it is reduced by 3, then we need to pay attention to the system. So the test needs to be repeated, or we need to investigate the reason. So the last test is about advanced MRI system testing. Just give two examples. This is not done everywhere, but the EPI basically look at stability. This is an important sequence for diffusion, perfusion, and functional MRI. So if your scanner is running these exams, so we recommend looking at the stability. And if spectroscopy also is not run on all the scanners, but if your scanner is running spectroscopy, then we recommend to scan a spectroscopy phantom. So you can see the typical peaks, Ho-Ling, creatine, NAA, lactate from the phantom. This is a typical annual QC report from our site. This is the first 2 pages, which is executive summary, listed all the testing I just mentioned. So this is a serve as a summary of my first part of the talk. So I think I only have maybe 2 or 3 minutes left. I just want to quickly mention.
As the topics is very important, and we started little later, you can finish your slide and explain.
Okay.
Thank you, sir.
Yes, you can take more time. Yeah.
Yes, sir.
Okay.
Yes, sir.
Yeah. Maybe I will plan to extend for 10 minutes. Is that okay?
Yes, yes, sir, sure.
Okay. So quality control testing is not everything for quality measurement. Here I list a different component of quality measurement. Equipment QC is what I just mentioned. But even with the QC all of the testing, there will be image quality issue. Also, MRI has so many protocols. An image quality issue can be related to protocol. It can be related to QC, meaning the equipment issue. It can be technical errors, many different kind of issues. And also service events. Service can cause some, usually will make things better, but can also cause some issues sometimes. MRI safety is a very important topic. And the next is the advanced applications. So all of those are very important to maintain a good quality of MRI program. So in the next few slides, I just want to, I think I will give a few examples and then spend some time on the protocol management or protocol optimization. This is an example of our daily QC system. I mentioned for every scanners, we do the ACR QC. And on top, this is a very small font, but this lists the 30 scanners. So very quickly, we can see which scanners are on, which scanners are down. And each line is one scanner. So MR13, MR14, MR15. And they are the result of the ACR measurement. And very quickly, we see there's a red flag there. There's a yellow flag there on a particular scanner. So physicists monitor this every day. Protocol is very important. Protocol consistency is very important. Many sites has protocol database, especially the academic institution in the US. We have that too. I'm just showing you one of the protocol. So everyone, including the technologists, they can go to the website and then look up this protocol. This is a diagnostic CTL spine protocol. You can see the protocol include 18 scans because it include 3 parts of the spine, cervical, thoracic, and lumbar spines. So many scans. For each scan, what's the FOV, thickness, spacing, metric size. And if you click into each line, it will give you more details like TR, TE, all the sequence parameters. So we can make sure every time this is run correctly. Also, there are some additional positioning tips for the technologists. Here, the example are where to place the saturation bands. So those are the protocol part. And we also have an image quality request and database. So when the technologists, they are on the scanner, or when the radiologists, they are dictating the images, they found the image quality issue, they can right-click on the image in PACS system. And then right-click, they can send out an email telling us there's an image quality issue. When they send out the email, all the physicists will receive the email. Also, there will be a line in this database. Okay, and then physicists in real time can just understand there's an issue on a particular scanner, on a particular protocol, and then we can try to solve the issue. So here are the white are the new image quality requests coming to the database. The blue are those ones have been we are under has been open. They are still open, and the green are closed. So the problem are solved. Okay, for the image quality, just like any other medical image modality, for MRI, the image quality means contrast, spatial resolution, noise, or SMR. In addition, there's artifact problem. Today, I don't have time to discuss artifact. Artifact will be a separate, maybe it alone will be a 1-hour lecture. But I just want to go through this quickly. So on the left-hand side are the primary parameters that can be manipulated by operator. Okay, TRT, inversion time, flip angle, slice thickness, gap, number of slices, field of view in 2 directions, metric size in 2 directions, number of average, bandwidth. Those are on the MRI console that can be changed by technologist. And then on the right-hand side are those related to image quality. Those are the results. There we can call them secondary parameters, including SNR. I mentioned resolution, contrast, but also scan time is very important for any scanners. Coverage is important. We want to make sure the lesions are covered. And our goal of optimization is to manipulate those primary parameters. They can be adjusted by operators to optimize the goal in the secondary parameters. So for example, for some scan, resolution is important. Then we can sacrifice scan time, or we can sacrifice noise to retrieve high resolution. For other scan, when the patient is moving or it's a pediatric patient, scan time is very important. We can sacrifice some resolution, or we can sacrifice some coverage. Okay, those are all trade-off in MRI, unfortunately. When you try to optimize one, usually we have to sacrifice something. But here has a very brief list of which parameters will affect image contrast, which parameter will affect coverage or SMR or resolution. Those are a little bit more theoretical. I want to skip those 2 slices. Basically, they describe the signal and noise from MRI. If you later on you have a question, you can email me or ask. But the 2 slides, after we have understand the signal and noise source from MRI, then we can describe this important equation. Okay, so this equation is basically derived from the previous 2. The SMR is proportional to proton density, of course, a number of protons within a certain volume. And then the voxel size. So that's the voxel size in each direction, frequency, encoding, phase encoding, and slice. And the number of samples, the metric size in the frequency encoding, phase encoding in a direction, and also the number of averages, and divided by square root of bandwidth. So this is very important. Bandwidth and SMR, they are inversely proportional. Square root of bandwidth is inversely proportional to SMR. And then it's proportional to the field strength and other parameters, including TRTE and coil used. Okay. So among all of those parameters, bandwidth is probably the least familiar parameter for most people. So I want to highlight a little bit about what's bandwidth. It is indeed in the parameter that can be adjusted, but many technologies, they are feared of bandwidth because they don't understand it. There are two kinds of bandwidth. First is transmission bandwidth, another is readout bandwidth. The transmission bandwidth is not adjustable on the operator user interface. So when we look at MRI console, the bandwidth means the readout bandwidth, okay? The readout bandwidth is 1 over delta TS, where delta TS is a sampling interval in the readout time. During the readout, delta TS is a sampling interval. In some scanners, so for example, on GE scanner, it describes this bandwidth. On the Siemens scanner, actually, it describes bandwidth per pixel. So bandwidth per pixel is just bandwidth divided by number of pixels in the readout direction, this NX, the frequency encoding direction. And if you plug in this to that equation, you know that's 1 over NX times delta T. What's NX times delta T? Delta T is one sample. NX times delta T is the total sampling time. So this is basically the total readout time, okay? So on GE, the bandwidth is inversely proportional to the one sample time. On Siemens, the bandwidth per pixel is 1 over the total readout time. So when we decrease the one, like I mentioned, one way to increase SNR is to use a smaller bandwidth, okay? So that's desirable to use a lower bandwidth. But what other will cause if we reduce bandwidth? So reduce bandwidth, increase SNR, that's good. But if there's a chemical shift artifact, that will enhance chemical shift artifact. It will increase the minimum TE because the readout time increase. So this will increase minimum TE. That's not good for T1 weighted image. Also, because the total readout time is increased, number of slices will be also less. So slice coverage will be less. So we have to understand those. Resolution is very simple. It's just FOV divided by a matrix. So that's very simple. When we increase a matrix size with the same FOV, we have better resolution, but that will decrease SNR. When we decrease FOV with the same matrix size, that will also make the pixel size smaller, better resolution, but that will decrease SNR. Also, when FOV is smaller, we can cause aliasing artifact. Like I mentioned, acquisition time is important. Unfortunately, when we want to have a better resolution or better SNR, usually we have to increase scan time. So understanding about scan time is also important. Those are the equation to calculate the acquisition time. Okay, basically TR times number of phase encoding times next. That's a phase being echoed, that's a 3D. If you want to reduce scan time, the easiest way is to reduce TR. You can see that TR are in the equation for all the sequence, right? It reduce TR, reduce acquisition time. But what else will be caused when we reduce TR? The SNR will be reduced because it has less time for T1 to recover. Slice coverage will be less. It will be good for T1 weighting, but not good for T2 weighting. So we need to understand all of those from the basic physics. This is my last slide. Slice coverage is also important. Many times we want to cover a lot of anatomical region, but what's limiting the slice coverage? We need to understand how much time is required to image one slice. That's the minimum time required to acquire one slice. Here I'm showing you a spin echo sequence. So 90, 180, and then we read the signal. So to complete the whole process, we need a T0. T0 is just a preparation time. It's typically very small. And then TE, echo time. Echo time is at the center of the echo, so we still have half of the sampling time. So to complete the whole process, will require TE plus T0 plus half of TS. That's here. And within the same TR, we can acquire multiple slices. So this is 1 slice, 2 slices, 3 slices, and then that's the next TR. So number of slices can be acquired is TR divided by this time that's required for 1 slice. Okay, so how to increase slice coverage? We can increase TR, right? If we increase TR, then the second 90 degree will be much later, then we can acquire more slices. However, if TR becomes too long, then it won't be T1 weighted imaging. So there's some limitation. Another way is we can reduce TE or we can reduce TS. For example, TS is affected by bandwidth. If you still remember, the bandwidth per pixel is inverse of total sampling time. So if we increase bandwidth, then the TS will be smaller. So that can allow more slices. So I go through this very quickly, just basically want to show if the fundamental MRI physics is very important. Once we understand the fundamental MRI physics, then optimization becomes only empirical. Okay, the summary is still, I want to show this again. We spent a lot of time today because this is a physicist's job to do the QC, but also there are other important components. Image quality, protocol, and MRI safety. They are all very important for the quality management of MRI. Okay, that's it.
Okay, thank you so much, sir, for your valuable talk, and it was a very interesting lecture. So there are some questions from the participants. Let's take them one by one.
Okay.
Shall we start?
Please ask
should I look at chat? Let me see.
Yes.
Yeah, I can read chat. Let me see. Starting from the beginning. How reliable is the Gauss meter?
Govt.
Application available in your mobile phones. I'm not sure. I won't use that. I'm not familiar with the Gauss meter, but basically there are 2 kinds of magnetic field. One is AC, another is DC. Many times when we are talking about the EM wave exposure, they are related to the AC field. So like the EM wave from the mobile phone, those are the AC field. But the MRI scanner is really a DC magnetic field. So we want to make sure what we are the equipment is reliable to measure the DC magnetic field. Okay. So for the medical purpose, I don't know what's available in the mobile phone, but we should purchase a reliable Gauss meter that can measure DC field. And also from those vendors, they have a specification very clearly tells you the range that can be measured as well as the precision that can be measured. We want to make sure, because we are not measuring the high magnetic field like 1.5 T or 3 T, we are measuring the fringe field, the 5 Gauss. Yeah, that's very like 5 millitesla. So we want to make sure the equipment is suitable for the low DC magnetic field. I hope that answered the question. Okay, the next one. Please suggest the product name of any QA kit and Phantom set that encompass the ACR recommended MRI QC test. Okay, MRI is actually this question MRI is easier than other X-ray equipment. We just need an MRI scanner, which is already there, and then the phantom. Okay. Gauss meter is something we need to purchase, but that's not for ACR QC purpose. Gauss meter is for acceptance testing. It will be good for you to have if you would need to do acceptance testing. But for annual testing, you don't need a Gauss meter. For annual testing, you just need the ACR phantom, plus the phantom for RF coil testing. Like I mentioned, RF coil testing and also the magnetic field homogeneity testing, those are provided by vendors. So make sure when you buy the MRI scanners, the vendor, they also provide those phantoms. Okay, those phantoms for field homogeneity testing and phantoms for RF coil testing. Once you have all the phantoms plus the ACR phantom, then you are all set. Okay, that's the second question. Yeah, if you want to ask further, you can add more in the chat. I will just go through one by one now. The next one is, please have you any image for your phantom in position to check. Position in MRI. I don't understand this question. For your phantom in position for check. Have you any image? Do you have any image for your phantom in position? Do you mean how to position the phantom? Yeah, I'm guessing how to position a phantom. If the question is about how to position a phantom, depends on which testing. Okay, I assume you are talking about ACR phantom testing. For other testing, for the for field homogeneity, just need to make sure they are at the isocenter. For the RF coil testing, you follow the vendor's guideline. Vendor should provide you how to position the phantom for each coil, because it's different for each coil. For breast coil, for spine coil, they are all different. So follow the vendor guideline. So what we need to pay more attention is about the ACR phantom testing. For ACR phantom testing, the most important thing is making sure it's in the center of the coil, and also the level is very important. We need to have a level to make sure it's level in all three directions. Okay. So by the way, buying a good level that's MRI safe, that's also important, but that's usually cheap. That can be buy in many places. The plastic level is important. Mm-hmm. Okay, the next question. In newer scanners such as Siemens era, if the center frequency change, the system does not run. If we need to check where is the center frequency displayed, should we use service mode? So the question is about when using a Siemens scanner, how to display center frequency. I don't remember exactly. In our protocol, it's already set. I think the best is to ask a Siemens application. They can tell you. If I were go there to explore, it shouldn't be difficult to find, but I believe in the MR spectroscopy. That's at least during MR spectroscopy, we can monitor center frequency. But I believe in other places, there are options too. I just don't remember right now. Okay, it shouldn't be difficult to find, but if there's any issue, you can ask Siemens applications. It's feasible. The next question is, please explain how central frequency fluctuation leads to quench. There are many reasons of central frequency fluctuations. Not every fluctuation will lead to quench. I should clarify that. Most of them will not lead to quench. Okay, but one possibility that can lead to quench is when the code head is malfunction. So if you know the MR hardware, you probably know right now the MRI is the main magnet coil is in the liquid helium, and modern scanners you don't have to refill that. Okay, so outside of the liquid helium there's a vacuum space, and outside of that there's coolant. So the code head will maintain the coolant, but if the code head is malfunction, then the coolant may not have proper function. So there's a risk to make the magnet heat up, and when the magnet heat up enough, that can evaporate enough of the helium, and then that can cause quench. So it's really not very difficult to quench. It's not, in modern scanner, it's not so easy to quench. Even if the coolant is not working for a day, maybe it's fine. However, if it's really bad for a period of time, for a week, maybe it can lead to quench. So when at that time, you will see a small fluctuation in the central frequency, but it can be small and consistent. That's the example I show here today. And the next question is, what is the software used for subtraction in SNR calculation? So like I mentioned, only when you use NEMA, you need to do subtraction. NEMA is a standard method, but it's not a required method. So you don't have to do subtraction. If you want to do subtraction, if you want to follow the NEMA method. So first I emphasize it's not required, okay? But if you want to do that, all of the vendor software, they can allow subtraction. In the, just in the console, you can subtract images. If you don't know how to do it, again, you can ask application of the vendor. But what's most important when using NEMA method is you want to make sure the calibration and the gain are the same between the two images. If you are recalibrate the second image, then you cannot subtract the two images. Okay, that's a key point when using a NEMA method. Okay, the next question. Please explain the quantum mechanical explanation, interpretation of magnetization, resonance, and free induction decay. This is really, I'm afraid this will be another lecture. This is a whole lecture. So may I allow to skip this question for now?
Yes.
Yeah, sorry about that.
Or any doubt, the participants can mail you. I will send you mail address to them.
Okay, sure, of course. Yeah. Next question is, are there any QA for MRI coils? Yes, like I mentioned, all the MRI coils need to be QA'd annually. And fortunately, all the vendors, they provide QA program that needs to be run under service mode. So the best is if physicists can have access to the service mode. That's very common in the US. I'm not sure in your country whether that's possible. But in the US, all the physicists have service mode. And under the service mode, you can run the QC program for each coil. So it turns out, in principle, testing RF coil is very complicated because there are so many different coils. For example, testing a 16-channel coil, it's so complicated you have to do it on your own because you have to measure each coil element. You will get at least 17. So 60 element measurement plus a composite image measurement. But vendor already make it automated. If you can go to service mode, you can just run through their program, follow their guidance to position the phantom properly, and then run it, and you will get the result. Okay, the next question is, does low contrast detectability depends on the precision of observer's eyes? Definitely, yes. However, when we do this assessment, you are allowed to change window level and zoom in and zoom out freely. Okay, so anyone, you can just try to, again, justify the window, and magnify it, and then see the best you can see. But still, even under that condition, if it's observed by different people, it can have different results. But rarely the result can be differed by 3 scores if we use ACR phantom. That's why ACR recommendation is if it's lower than 3 scores, then you need to pay attention. Okay. And the next question is, what are the reasons behind magnetic field drift? Magnetic field drift usually, so there are 2 things. One is when the system is not running, it's just drifting. This is really uncommon. We don't usually see that, but it's only common during the new installations. During the new installations, the system is just not stable. So during the ramp-up procedure, there are many considerations. It's not stable. It needs to be stabilized. I don't have time to discuss all the details. But if it's not a new installation, we don't usually see field drift. The field drift indicate an issue, usually related to cold head or some issue related to power supply. So that's one. Another is doing scanning. If we are using a certain pulse sequence that runs a lot of gradient. So for example, EPI sequence, when we are doing a long functional MRI scan, for example, and those fast switching gradient will hit up the metal surrounding. So there are some shimming metals. Again, this goes into very details about the shim, how shim is done. But there are metals, and the gradient will cause eddy current that can cause heating in those metals. And those heating of the surrounding metals can also cause a local magnetic field. So that's a very, it's not uncommon to observe a magnetic field drift if we are running a high switching gradient pulse sequence. I assume you are not asking about that, but I just thought to mention. Okay, the next question is, what would be the optimal bandwidth for a brain spectra to study GABA? Bandwidth, let me about it. I don't use, GABA is not a clinical protocol, so frankly, I don't have experience with GABA, so I need to think from the physics. But I don't know if there's a spatial considerations. Maybe if there's expert here already doing GABA can provide. I would just say the bandwidth that can allow you most SMR, which is the smaller bandwidth. If you understand the spectroscopy, we cannot have frequency encoding gradient during the readout. Okay, so it's not related to the readout gradient itself, but it's just a sampling time. Okay, so just talking about the sampling time, we want the smaller bandwidth, but the smaller bandwidth can affect TE. As I mentioned, the smaller bandwidth will increase the acquisition time. So that can affect your minimum TE. Again, I'm not familiar with GABA detecting, but if you require a small TE echo time, then you may reach a limitation when you shorten the bandwidth. That's what I can think about from physics. Again, I don't have experience on this. Sorry about that. And the next question is, what is difference between FID and T2 decay? FID is based on T2 star decay. So the question is probably difference between T2 star decay versus T2 decay. So T2 star decay include T2 decay plus the spin dephasing caused by field inhomogeneity. If I can write the equation, that's a delta B. So T2 star decay is faster than T2 decay because it includes additional field inhomogeneity, that's delta B. And I can go into even more details, but I don't think I have time to describe the mechanism of T2 decay spin-spin interaction versus the delta B field homogeneity. But that's a primary difference. The next question is, what books do you recommend for fundamental physics of MRI? For medical physics education, our textbook is usually Bushberg. I don't know if how many of you know the textbook. That's the most common textbook for imaging physics in the US. That textbook includes every modality, not just MRI. MRI has 2 chapters in the book, but those 2 chapters are enough for general medical physics practice. Okay, not MRI specialty, but general MRI, general physics practice. If you talk about MRI specialty, there are 2 other textbooks I will recommend for physicists. One is by Hickey. It's a big book. I don't remember the whole name. And another is called MRI Handbook. There are two authors, Kevin King, Joe Zhao, and who else? I forgot. But if you like to know them, you can email me. There are 2 other textbooks that are specific to MRI physics. Okay. The next question is, what is the recommendation about value in slide 5? Which slide is slide 5? Slide 5 is RF shielding. Okay. Yeah, so if the question is about RF testing, okay, RF shielding testing, what's the recommendation about the value? So the limit is 100 dB attenuation across different frequency tested. Okay, I mentioned that. It's also highlighted in my slide. That's about RF shielding testing, 100 dB attenuation. What's the next question? We are using MR image for fusing with CT image in radiotherapy. How can we be assured that MR image are good enough for fusing with CT image in radiotherapy? Oh, this involves a lot. Again, this will probably be a separate talk because MRI for radiation therapy, there are different considerations. But first of all, we want to make sure that geometric distortion is minimized. So that needs to be done by the front end, by the protocol part. We want to make sure the bandwidth is larger. So any distortion, amount of distortion depends on bandwidth. With a larger bandwidth, the distortion will be smaller, but the SNR will be lower. So that's the optimization part. Also, most of the modern scanner, they have distortion correction that correct for the gradient nonlinearity. So you want to make sure in your protocol, the distortion correction is turned on. If it's a 3D image, many of the MRI guided MRI used for radiation therapy use a 3D image. You want to make sure the 3D distortion correction is turned on instead of 2D only. So distortion correction is very important. That covers, so the bandwidth covers the field homogeneity, cause the distortion, and the distortion correction covers the gradient related distortion. And then the next question is the imaging resolution, whether the resolution is good enough for the software to fuse. And for that part, you really have to make sure the software requirement, and also depends on anatomy. Typical resolution we require is about 1 millimeter, but for certain anatomy, probably you don't need 1 millimeter resolution. And then the next is whether the software perform properly. That's another topic. You need to test the software, not just test the scanner itself. Yeah, the software testing is a new topic in the medical physics field. So I don't have much to talk about that because it's brand new, but that's a very important topic to make sure the software is operating properly. Hope that covers the question.
Yes, sir. Thank you so much for answering all the questions one by one, and you make the topics very interesting and easy for the participants.
Okay, that's good. And there are more questions here. By viewing MR image, how can we assure that image quality and resolution optimal? So you are talking about optimization. I assume it's not the QC testing. QC testing has certain criteria. We imaging at 1 millimeter, we want to make sure it has 1 millimeter resolution. But you are talking about optimization. That really depends on clinical applications. For clinical applications, the way to image, the way to make sure quality is optimal, it's very simple. We ask radiologists to review. It's not determined by physicists. Okay, whether the image quality is optimal, you want the radiologist to confirm. So we routinely have a QC meeting with radiologists to review image quality in different protocols. And during that meeting, they can tell us whether the image quality is good or not, and then what's their desire, whether they want better contrast or they want better resolution or better SNR. Then we can try to fine tune our protocol. So that's about image quality optimization. The next question is what's meant by ghosting in MRI and how it affects image quality. Ghost means anything that's unstable. Unstable means the system is changing during the scan. So what's changing during the scan? There can be many things. It can be hardware. For example, the receiver chain, the receiver sensitivity of the detection is changing. Or it can be physiological. Blood flow is changing during the scan. So either one can cause ghosting. When the system is changing during the scan, then you will see some image intensity along the phase encoding direction. That's called ghosting. So when the ghosting is overlapping in anatomy, of course, that can affect the diagnosis. That's not good. But if the ghosting is outside of the anatomy, usually that won't be a much issue. So like motion will cause a lot of ghosting. Okay, I think I probably reached the last question. Please give me guidance how to be a part of the residency program in imaging in MD Anderson. And what's the requirement, eligibility? So in the United States, all the residency programs are CAMPEP accredited. So to enter a residency program, you need to fulfill the CAMPEP requirement. I encourage you to look at the CAMPEP website. The basic requirement to enter a CAMPEP accredited residency program is that first, if you are graduated from a CAMPEP accredited graduate program, so if you obtain a master's degree or PhD degree from a CAMPEP accredited program, then you can apply for the residency program. I assume most of you probably are not from the graduate program that's CAMPEP accredited. Second path is that if you are not from a CAMPEP a master or PhD program, you can enroll in a certificate program. A certificate program usually is a 1 year long, so you can take the 1 year. That's also CAMPEP accredited certificate program. And once you complete the certificate program, then you can also apply for the residency program. That's a second option. The third option is you can take certain courses from your graduate program and then ask CAMPEP to certify your course. That's very difficult, okay, to certify individual courses. For example, there are 5 courses required, and then you want CAMPEP to certify your individual course from your program in your country. That's a possibility, but it's very difficult. Okay, so there are those three pathways.
Okay, sir. Thank you so much for your valuable lecture and your guidance. So I would like to invite Zachariah sir to say something. And
yes, before I say something, Madam Azari, do you like to say something?
Many thanks, Dr. Anthony. So just give you huge explanations because they're very important, and we can take divisions of the MRI because MRI can be a one course like this, different parts. So we are in mind because this time we have given all the imaging methods, but we are thinking in the futures that we can have each topics differently. And then and your explanation is very good, and I think everybody has joined. Many thanks, and please keep it. I will keep touch with you because for a symposium, you will be a very good speakers for us. Thank you.
Sure,
yes.
you're welcome.
In addition to that, I think it is a very, very interesting lectures for those people who want to start quality control in MRI.
Yes.
Or it is a refresher course for those people who is already doing the quality control. Anthony had to explain very slow and good, and I think you have understand many of the points. When you have problem them points, he has given 2 reports. You can actually read these reports, and what is important always a teamwork. Ask your colleague in other hospital, maybe visit them and make it clear. This is I think is the most important modality of imaging because it has huge potential. Yes. He has also showed you we have some spectroscopy. Yeah, maybe one day we can differentiate between malignant and benign tumor. Yeah, these are all potentiality. So I think a medical physics must be an expert to this imaging modality. This is, I think it is a very fascinating lectures, and you have learned a lot. And he also offered you, when you have special question, please ask him directly. Thank you once again, all the participants. You have still 30 people is here. Yeah, we have almost 2 hours. So the topic is so interesting that everybody is here. Thanks also Sharma, Gunjan Sharma for your moderation, and of course the SCMPR team, and last but not least, the participant. Without participant, no lectures. So the participants are very, very important. Thank you once again, Anthony, and meet you tomorrow. I hope you have also tomorrow time to discuss once again.
Sure.
Yeah, thank you.
Can you please share the email address of the Anthony, sir?
Yes, we can do that.
I will send the participant.
Okay, thank you
I
for
would
such
like to
comprehensive
today.
lecture.
Yes.
I would like to end today's session by thanking our chairman, sir, and the entire team of SCM PCR, whose efforts have made this session a success. Thank you all the participants. We appreciate your presence here. So tomorrow is the group discussion with our speakers. So we will be waiting for all of you tomorrow, same time, same place. See
Yes,
ya.
and
Goodbye.
I would like to encourage the participants to ask your doubts and questions from the previous lectures also. There will be present all the speakers, and I hope you will make the group discussion session interactive.
I am already late. Today is the German and Portugal football. It is 15 minutes over. Please join the football. Germany against Portugal.
Okay, sir. Enjoy the
Okay,
football
sir.
match. Thank you, sir.
Can you
Thank you
please
so
tell
much.
us what kind of examination will be conducted at the end?
Yeah, there will be a MCQ type questions, 25 MCQ questions, 5 questions from each speakers. The questions covers the lecture of the course.
Those questions will be only from the lecture contents.
Yes. Please go through
Okay,
the
thank
lecture contents. Yeah.
Okay,
And
thank
I
you.
will
Thank you.
give the instruction to the participants how to proceed the examination and the procedure.
Okay, sir. Okay,
Bye-bye.
thank you.
Sir, would you like to please share the recorded lecture?
Yes, I will send all the
It will be
recorded
shared.
lecture one by one.
Okay, thank you, sir.
Okay, thank you. See you tomorrow.
Thank you so much, sir. See you
Thank you,
tomorrow.
sir, very much.
Bye.
Good night. Take care.